Hello everyone. Today we are starting with a new unit of wave optics. In last theory we studied about ray optics, or rather you can say we studied about ray theory of light. And ray theory successfully explained reflection, refraction, dispersion through a prism, scattering of light. These are all phenomena that we have studied using ray theory of light. There are still few phenomena of light that cannot be explained by ray theory, that are interference of light. Interference is simply superposition of waves that we have studied in 11th, and we'll see interference in quite detail. And diffraction of light. Diffraction is the bending of light when light passes through an obstacle. A very routine example of diffraction is the light coming through the window of our room. If light actually travels in a straight line like ray does, then light coming from the window should travel in a straight line, and we should only see the light that is in the straight path from the window. Actually what we see is that light, when it enters from the window, it spreads in every corner of the room. Okay, if this is a sample room and let's say there's a small window, and if light actually travels like a ray, then it should only travel in a straight line and should illuminate a very small portion that is exactly opposite to this window. All right, but what we see that when this light enters through a small opening or a slit, you can say, it spreads in every corner. We can see the ceiling and the side walls and everything in this room. That means light bends. If it is actually ray, then it should not bend if it does not change its medium. Well, actually rays bend when they pass through a small opening. This is diffraction, slightly different from the refraction, that is the bending of ray when it changes the medium. Light also changes its or bends even when it does not change the medium, but when it passes through the small opening. This is diffraction that ray theory could not explain. We also studied polarization, we'll study. So these are different phenomena that ray theory could not explain. Even Newton tried this in his corpuscular theory, but even this theory failed when he suggested that light is made up of large number of tiny particles called corpuscles, and they should travel, they should follow all laws of mechanics, like carrying the energy and momentum and the rigidity, etc. But even this theory of Newton, corpuscular theory, could not explain Newton diffraction and polarization of wave. So that's why Huygens suggested, another scientist in almost similar era of Newton, around 1650, gave wave theory of light. And with this wave theory of light, we could explain all phenomena that we are seeing in daily life, like light coming through a window, or even the interference pattern in a dark room that lab shows, or even the polarization of Polaroids our daily life use. All these phenomena that are observed either in lab or in daily life could not be explained by ray theory or even Newton's corpuscular theory. However, if we study wave theory of light, then we can explain all these real life or laboratory phenomena of wave. Okay, that's why we are studying another theory related to the propagation and the energy carrying capacity of light, that is called wave theory. So ray and wave theory both have their own significance. They both explain different characteristics or the nature of light. Ray explains reflection, refraction, dispersion, scattering, etc. These are all phenomena that are very well explained by ray theory, and it is easier also. But there are certain phenomena that ray theory or the corpuscular theory could not explain. So that's why we are starting with the Huygens principle or Huygens wave theory, that will give us more idea about the study or the propagation of light. Okay, so that's why we are starting this new unit today, that is wave theory. Now before starting this wave theory, we'll first go through some basic terms related to this wave theory of light suggested by Huygens. And first is the idea of wavefront. Okay, now to study wavefront, you need a very basic idea of wave that we have studied in 11th. And what we have studied is that if we draw a displacement distance graph, then any wave that travels in the form of crest and trough are called transverse waves. All these particles are at crest, these are at trough. The distance between two consecutive crest or trough is called wavelength. These are very basic things that we have studied in 11th standard already. What we also know, that distance traveled to complete one circle, one complete cycle, is wavelength, and one wavelength has phase difference of 360 degrees or 2 pi. That means what we know is that 1 lambda or 1 wavelength gives 2 pi radians of phase. Okay, so that means this particular point, let's say this particular point should have phase difference of 2 pi. This 2 pi. If we continue this wave, this should also have 2 pi. That means every lambda meter of distance on a wave gives 2 pi of phase. But what if we choose wave somewhere at an arbitrary point? This is the particle. Then what we know, that this is one wave, 2 pi radian, half the wave, pi radian, this is somewhere in between. So what is the phase at this random point? Then what we have taken, we have taken that the distance of this random point from the origin is x, and we applied unitary method, that if 1 lambda gives 2 pi radian, then any arbitrary distance x meter, because lambda is in meter, gives how many radians? Okay, if lambda meter gives 2 pi phase, then x meter give what is the phase? Then if we cross multiply, what we get? 2 pi into x divided by lambda should be the phase at that random point denoted with phi. Okay, so equation of phase is 2 pi by lambda into path, or you can also say phase difference delta phi is 2 pi by lambda into path difference delta x. Remember, we have not started still with the wave theory that we are going to study in 12th standard. This is all basic idea of 11th that I am discussing, because these are important for the wave theory of light. Okay, so what you have to remember is that these are transverse wave, these are all crest, trough, distance between two consecutive crest or trough is wavelength. One wavelength give 2 pi radian. So any random arbitrary meter will give some phi radians. So if we make phi the subject, it is 2 pi x upon lambda. If we take phase difference between any two random points, then it will be 2 pi by lambda and the path difference between these 2 points. Okay, so very important equation in this class would be, this is the concept of 11th standard, phase difference is 2 pi by lambda into path difference. Correct, this is important that we are covering in this class. Okay, apart from this, what else you have to study, is the concept of wave front. There's again something new that we are starting today. Let's understand this with a small animation, and let's see that if we release a stone in silent water, what we see, there are ripples generated on the surface of the water from the source of disturbance, and these ripples are spreading outward. If we take a random point that is at certain distance away from the source, then this point will also oscillate, and that point is at some distance r. These are traveling in the form of ripples, so they create a circle. And what we know, that every particle on this circle will be either at crest or at trough. Again, this is where the stone is dropped. We see that ripples generated on the surface of the water, and these ripples are traveling in the form of crest and trough. They are traveling in the form of crest and trough. This is how waves propagate on the surface of the water. Right. Now, if we take any arbitrary point on this circle, then this all particles will be at crest. See, all these particles will be at crest. These are arbitrary choices that are made, that are all particles at crest. You can also choose any random point in between. You draw a circle here, then all particles will be at crest. Okay, for reference only, this is the point of disturbance. And what we see that all these particles are at crest. Now apply that concept of 11th standard. If these are transverse waves that are generated on the surface of the water, and if we say one or two particles all are at crest, all are at crest, then what we know, difference between two crest is called wavelength, is called wavelength. Both these particles are at crest together, they will also go at trough together, that means they oscillate together. If these two particles oscillate together, that means path difference between them is zero. You can also study this from physics, from basic mathematics, because these are the points on circle. Its distance from the center would be same. So if we take P somewhere here, Q here, then its distance from the center would be same. If their distances are same, then path distance will be zero, path difference, that is delta x. And what we have studied in previous slide, the delta phi, phase difference, is 2 pi by lambda into path difference. If all particles on this circle are at same distance, same path, then path difference is zero. If path difference is zero, that means phase difference is zero. That means they are at same phase. That's why I was saying that all particle on this circle will be at same phase. Same phase, that means they are either all at crest or all at trough. Okay, so if we pass an imaginary surface through all these points having same phase, that is called wavefront. Locus of all points having same phase is called wavefront. This is the first terminology we are studying in wave theory. Wavefront, we have to draw a locus of all points having same phase. Same phase, that means phase difference zero. If phase difference is zero, that means path difference is zero. Path difference zero, that means they are at same path or same distance. Same distance from the point of disturbance should be a circle. Okay, that's why all these wavefronts are circular in nature. Okay, all these circles that we are studying are, all these wavefronts are circular in nature. These are called circular wavefronts. These are called circular wavefronts. Also, what we know that from the source of disturbance, these circles are spreading outwards. See, from the point of disturbance, these circles are spreading outward. So if we draw an arrow showing the direction of wave propagation, direction in which these waves are spreading is called ray. So these lines that are emerging from this wavefront are called rays. Rays are lines that indicate the direction of wave propagation. Again, see, these waves are spreading outward. So if we draw an arrow shown in the direction of this wavefront, then it shows ray. And the surface, water surface creates wavefronts that are circular in nature. If we place this source in space, let's say antennas on your terrace, then all these sources will generate energy in all three dimensions that are called spherical wavefronts. Okay, so it should be clear with the concept of wavefront. It is the definition: locus of all points having same phase. Same phase, that means phase difference zero. Clear? So this was a small animation that will show the waves generated on water surface or in free space. On water surface, they are very circular in nature. In free space or in any three-dimensional space, they will be spherical in nature. And wavefront is the locus passing through all points having same phase, right? So these are the points that it shows, the wavefront. See, wavelet, and this is the definition: locus of all points having same phase of oscillation, while ray is a line perpendicular to wavefront. Ray shows the direction of wave propagation, like in that animation. If you remember, we had a circular wavefront and we had rays emerging that are perpendicular to the circle, and they show the direction in which these waves are propagating. So that's why we say that ray is perpendicular to wavefront. line perpendicular to the wavefront is called ray. And we have various types of rays, or rather wavefronts. That is, these are all spherical wavefronts. And remember, these blue circles are spheres. Wavefront. Lines perpendicular to wavefront are rays. These are all rays. Okay. Similarly, if you have a line source, then every particle on this line will act as source of a radiation. Then they generate energy in all direction. And if we draw locus of all points, this will be cylindrical wavefront. These blues are a wavefront that are cylindrical in nature. If rays travel in straight line, then we also have plane wavefront. See, in every single figure, ray is perpendicular to wavefront. See, see here also. This is the ray that is perpendicular to wavefront. Okay, so this is the introductory term that we have discussed through that small animation. That means we should be clear with the concept of wavefront. Locus of all points having same phase or same path. Phase difference 0, path difference 0. If we draw a line in which this wavefront propagate is called ray. Ray is always perpendicular to wavefront. And these are various types of wavefront: spherical, cylindrical, plane. And in each type, ray is perpendicular to the wavefront. Okay, so this is the introductory term related to the Huygens wave theory that was slightly superior to the Newton's corpuscular theory. After all this introduction and the fundamentals, now we are starting with the Huygens principle. This is the actual wave theory suggested by Huygens in around 1650. And what it shows, that every point on a wavefront, that spherical, cylindrical, plane, any type of wavefront, acts as a secondary spherical wavelets which spread in all directions, actually in all directions, but we are considering forward directions only. The new wavefront is the tangential surface to all the secondary wavelets. Slightly complicated statement, lots of new terms like in forward direction, secondary wavelets, etc. Let's understand this also with a small animation, because they are slightly difficult to imagine on PPTs and board. So that's why I have tried to include the animation that will show you the 3D, three-dimensional generation of wave. Let's see what this shows. That this is the actual statement of Huygens principle. Then it suggests that each point on a wavefront is a source of secondary disturbance, and it generates spherical secondary wavelets which spread out in all directions, and they spread with the speed of light. If we draw tangent that is common to all these secondary wavelets, then it gives the new position of wavefront at some time t, at some later instance t, and this will give you the new wavefront or the secondary wavefront after time t. Okay, let's see. See, this indicates this source that are generating spherical waves in space. If we consider its cross section, it appears circular, and this AB is the wavefront, circular wavefront, and it is the cross section. Now what it shows, that every point on a wavefront, these are the points, every point on a wavefront acts as secondary source of spherical wavefront. That means every point on this wavefront can generate spherical waves, spherical wavefronts in all direction. See, every point on this primary wavefront generates spherical wavefronts in all direction. They travel with the speed v. So distance traveled is speed into time. And if we draw tangent to all these secondary wavefronts, tangential surface to all the secondary wavefronts is the new wavefront after time t, that is denoted with a dash b dash. Correct? Similarly, again, every point on a primary wavefront acts as the new source of spherical wavefronts. They all generate spherical wavefronts in forward direction. They also generate in backward. If we draw tangent to all these secondary wavelets, then we should also get some wavelet backward. Okay, but we don't consider these backward waves because they vary as 1 plus cos theta. They vary as 1 plus cos theta. If we consider backward waves from the original, then backward will have 180 degree. If we substitute this 180, then cos 180 would be minus 1. So 1 minus 1 is 0. That's why we say that backward radiations are eliminated, backward radiations are not considered. Okay, so this for the animation purpose we have shown that every point on this wavefront acts as new spherical source secondary wavefronts. If we draw tangent to all these spherical wavefronts, see, tangential surface to all these secondary wavelets gives new wavefront. So ideally we should have tangents in forward direction as well as in backward direction. But these backward direction tangents or the secondary wavelets in backward directions are neglected due to this reason. If you don't show this reason, that is okay. If you show this, that will give you more intense discussion regarding Huygens principle, but you should know. So that's why in the statement it is given that secondary spherical wavelengths spread out in forward direction. Actually they spread in all direction, it's just that due to this reason backward directions are not considered. Okay, now if we continue with this, then it shows that all these secondary wavelets, all these secondary backgrounds, or rather the wavefronts in the backward directions, are eliminated. Correct? So these are all secondary wavelets and the Huygens principle that it shows. Correct? See, and these are the rays that are perpendicular to the wavefront. This backward are 180, that's why we do not consider. So now in this part of animation, see, every point are generating spherical wavefronts, but only in forward direction. And if we draw tangent to all these secondary wavefronts, tangential surface to all the secondary wavefronts gives new wavefront. Okay, we can have that same discussion on a plane wavefront also. On a plane wavefront also, where all these points on a plane wavefront, all these points on this plane wavefront will generate secondary wavelets that are also spherical in nature. See, this is AB surface. Again, we are considering points on this primary wavefront. These points generate secondary source of spherical wavefront. But now we are considering only in forward direction spherical wavefronts, right? And then if we draw tangent after time t, where they have traveled the distance speed into time, if we draw tangent, this should give new wavefront after time t. Correct? So this is the secondary wavefront. This is how this Huygens principle relate, and this is how the wave theory of light goes through. This is the principle that was found superior than the Newton's and the other theories suggested for the propagation of light, that is the wave theory. So you should be clear with the wavefront. Ray is perpendicular to wavefront and the Huygens principle. And what this principle suggests is that now you should be clear after this animation that every point on the primary wavefront considered as a source of secondary spherical wavefront which spread out in forward direction. Again, I'm repeating this. They spread in all direction. It's just that backward directions are eliminated at the speed of light. And if we draw a tangential surface to all the secondary wavelets, we get new wavefront after time t. Okay, so this is a very important theory, Huygens principle, and this was the animation that we have covered. And this is how you can include in your notebook or in your reference. A normal source, these are rays. If we draw a tangent, these are all primary wavefronts, and what we know that every point on this primary wavefront will act as secondary source of new wavefront. Secondary sources are always spherical in all direction, but backward are eliminated. So if we draw a tangent, see, if we draw tangent to all these new spherical surfaces, this should give us new wavefront. Correct, this is spherical. As they spread out in nature, as they spread out in nature, their curvature decreases, and after a long distance, they almost appear flat. They almost become parallel wavefront. Here also same theory can be applied. They act as secondary source of new spherical wavefront. Backward are eliminated. If we draw tangent in forward direction, we should get new wavefront. Okay, this is parallel wavefront. So these are spherical. As they spread in free space, their curvature decreases. See, initially their curvature is greater, and as they spread in free space, their curvature decreases, and eventually they become parallel wavefronts. Okay, so this is how they travel in free space. Okay, every point access fresh source of new wavefront, and a new wavefront at any time t is obtained by taking the forward envelope, that is the forward curvature, forward arc in the secondary wavefront at that particular instance of time. And this is the reason by why backward wavefronts are rejected. See, we have already discussed this half into 1 plus cos theta. For backward direction it is 180, cos 180 is minus 1, and it is 0. Okay, so this is the first theory of wave optics, that is Huygens principle of secondary wavelets, or the Huygens theory, that is wave theory of light, suggested in around 1650. Okay, so how it is superior? We discussed in the initial part of this lecture that ray theory could explain reflection, refraction, dispersion, but it could not explain dispersion, interference, diffraction, etc. Interference, diffraction, and polarization. Okay, however, Huygens wave theory is spread and it is widely accepted because this wave theory also explains ray theory concepts, that is reflection, refraction. These are very well explained by ray theory, but ray theory had its own limitations. It could not explain interference, diffraction, polarization. However, wave theory explains all phenomena. Wave theory explains reflection, refraction, interference of light, diffraction of light, polarization of light. So that's why this wave theory is widely accepted and it was found superior. And this is the fundamental that we are seeing on the screen right now. That is the Huygens principle and how all these waves actually propagate in free space. Okay, so one by one we'll discuss all these phenomena using wave theory in this unit. So we'll start with reflection and refraction, then we move on to interference, diffraction, polarization, all explained by this wave theory of light. And this is actually our overview of the unit. These are the points that we'll be covering in this particular unit. Okay, so in today's class we'll discuss reflection and refraction of light using wave theory. We have already justified this with ray theory, but we'll explain this with wave theory. Okay, now this is the figure. This is, we are trying to justify or prove refraction of waves using Huygens principle. In exam also, you will get this clearly mentioned that you have to explain refraction using wave theory or ray theory. Okay, here it is clearly mentioned. We have to discuss refraction using Huygens principle. Since it is refraction, there should be a change in media. So this is the ray traveling from one medium to the other, and we have taken that refractive index of 1 is less than the refractive index of 2. That means this first medium is taken as rarer, second medium is taken as denser. So if we consider this ray theory, as it travels from rarer to denser, it bends towards normal. Okay, so we don't have any problem with this ray theory of light. Now we'll discuss this with wave theory. What we know, that if this is the ray, these are rays, then wave should be perpendicular. We have seen in the introduction part that a wave is perpendicular to ray. So this is the wave incident on an interface. This is the interface because it is the boundary that separates two media. So when this incoming wave strikes this interface separating two media, then what Huygens principle suggests? That every point will act as secondary source of new spherical wavefront in forward direction. So the moment this incident wave strikes this interface, this particular point will follow Huygens principle. This will generate secondary spherical wavefront. So what I am doing is, I am taking this point as reference and making an arc. Correct, this is the spherical wavefront in forward direction, very similar to that animation that we have discussed. This point upon striking will generate secondary wavefront in forward direction. What should be the radius? Speed into time. Okay, but this is in denser medium, so it is V2, right? Similarly, when this point A has reached first interface, this B point is yet to reach. B will have to travel some extra distance to reach that same interface. So now what is the extra distance traveled? Again speed into time. But this is the distance in medium 1. So its speed is V1 into t. Okay. This A has already reached the second media. So it travels with speed into time, but speed in denser medium is V2. That is less because it is denser. Now this B will have to travel some extra distance to reach that same interface. It is still in medium 1. So now the extra distance traveled by this B is again speed into time, but since it is in medium 1, it is rarer, it is slightly faster, it is V1. So that speeds are different. That's why I mentioned V1 and V2. Okay, so after this theory, we simply have to apply basic Trigo rules. Now consider triangle. I'm writing theory. You can write down all these mathematical steps in your notes also after drawing the figure. Consider this triangle. That is triangle BAC. BAC and apply sine I. Sine I. So I's opposite is BC. BC is B1T. Upon hypo, this is right angle. So the hypotenuse is AC. Equation 1, simple sign. Now take this triangle ECA. Triangle ECA. Again apply sine. This makes R, angle of refraction, sine R. Sine R's opposite, V2 into T. Upon hypotenuse, see this is ray, this is wave, these two are perpendicular, AC is hypotenuse. Equation 2. So we get equation 1 at angle of incidence. We get equation 2 at angle of refraction. Now take ratio. Take 1 upon 2. So what we get? Sine I upon sine R. If we take ratio, then AC cancel, T cancel, 1 upon 2 is V1 upon V2. Now what we know is that refractive index by basic definition is C upon V. C is the speed of light in free space. So we know that N and V are inversely proportional because C is constant. N and V are inversely proportional. So N1 upon N2 is V2 upon V1 because N and V are inversely proportional. Apply this equation or this relation in our equation. What we get? LHS sine I upon sine R. What is RHS? V1 upon V2. V1 upon V2 should be N2 upon N1 because N and V are inversely proportional. This is V1 upon 2. We should get N2 upon 1. Apply cross multiplication. What we get? Cross multiplication. N1 sine I is equal to N2 sine R. This is Snell's law. We have studied this in ray theory. This is Snell's law. So this same relation we have obtained, that is Snell's law. We have nicely studied in ray theory, but still we derived this using wave theory. So wave theory is all inclusive. It describes every possible phenomena of light using wave theory. Okay, so if you have to write refraction of waves using wave theory or Huygens principle, you need to draw this figure, write down few considerations and all these mathematical steps that we have covered. Okay, I in rarer medium, so it is N1 sine I, R in denser medium, N2 sine R. See, okay, so this is the refraction or Snell's law proved using Huygens principle or wave theory. Okay, similarly, we can also discuss reflection of light. See, reflection of light using wave theory. We have studied this in ray theory. Okay, again see, since it is reflection, this medium is shining. This is the incident ray. It will reflect back with same angle of incidence, we know. But we have to prove this with wave theory. Now, this is incident ray. What we know that wave is perpendicular to ray. So these are rays incident. You can show many rays also. I have drawn two. These are two rays. Wave is perpendicular to ray. So this is the incident wavefront. Again apply Huygens principle. The moment this wave strikes this media, strikes this reflecting surface, this point will act as secondary source of new wavefront. spherical wavefront. Since it is reflecting, it reflects back that same secondary source of spherical wavefront, see, like in that animation. In previous theory, it was refraction. So it was traveling into the other media. It was traveling into some denser medium. This is reflection. So it is reflecting back into the same medium. So the moment it strikes, this point A on a wavefront will act as secondary source of new spherical wavefront. What should be the radius? Speed into time. It is the same medium. Now, when this A has reached this reflecting surface, other point on this wavefront B is yet to reach that surface. So again, it has to travel some extra distance. What is the extra distance required for this B to reach this reflecting surface? Speed into time. Correct? So in previous theory, this was V1, A was traveling into other mediums, it was V2. This is reflection. So reflected and incident both are in the same medium. So there is no question of V1 and V2. Okay, after doing this, apply simple tree group. We have to write for I. So take a triangle BAC, write triangle BAC and apply sine I. Sine I is opposite VT upon hypo. This is perpendicular, so this hypotenuse is AC. Equation 1, simple rule. Then we have to write for sine R. So take this triangle ECA. Okay, same triangles. ECA. Now write for sine R. See, this is ray wave, this is perpendicular. Sine R. R is opposite. VT upon hypotenuse. AC. This is equation 2. Okay. Again, like previous theory, take 1 upon 2. If you take 1 upon 2, VT upon AC cancel. That means sine I upon sine R is equal to 1. This implies that sine I equal to sine R. If you take sine inverse, this also implies that angle I is equal to angle R. Angle of incidence is equal to angle of reflection. We know. Okay, this is the same theory, same law of reflection that we have been studied from 9th or 10th standard. That same law of reflection is proved using wave theory, using Huygens principle. Okay, very simple mathematics. So this is how this chapter goes. If you understand the basics, what are wavefront, ray, how Huygens principle is applied, how spherical wavefronts are generated in forward direction. That's why I've included few animations. If you are clear with the concepts, the rest of the chapter is relatively easy. We have to study 6 phenomena in this chapter: refraction, reflection, interference, diffraction, polarization. That is 5. Out of 5, we are already through with 2 phenomena. Okay, very simple theory. Same law of reflection we have used with Huygens principle. Same Snell's law we derived using Huygens principle. Okay, so this is the first part of wave optics. Few introductory terms: wavefront, phase difference, path difference, Huygens principle. If you are through with Huygens principle, you have understood that concept nicely, then the chapter should be easy. Okay, not lengthy chapter, but easy. Okay, few numericals would be there, but relatively easy. So we have to study refraction. We have studied, we proved Snell's law using wave theory, and we studied reflection of waves. We proved law of reflection using wave theory. So this is the first part of this lecture. In our second class, we'll start with the interference concept using wave theory.